Hey, welcome back everybody. Now that you're familiar with the fundamentals of Boolean algebra, including the and or operators, we're going to look at how that applies to circuits and switches. As it turns out, electrical switches and simple circuits give us a great way to visualize what's going on with Boolean algebra. So we're going to look at how those operators are represented by basic switches in this lesson and look at some simple circuits. So let's get started. So for starters, what is a circuit? Well, a circuit is basically just a closed loop that allows electrons or power to flow through components that we usually call loads. And we're going to represent loads with just little light bulbs in our animations here. So if you look at the circuit that's on your screen, it's about as simple as it gets. There's a power source on the left side that represents the symbol for a battery. And there's a switch at the top of that circuit and a light bulb on the right. And of course, as you'd expect, when the switch is closed, then we would say that that's a condition of 1 in Boolean algebra. And when it's open, we represent that with a 0 in Boolean algebra, which means there is no electron flow. Now there's two main ways that switches can be arranged to work together with one another. The first way is when switches are in parallel. We say that they're in parallel because, as you can see in our little animation here, they run right alongside each other. They are parallel to one another. So we know that switches that are in parallel complete a circuit when either one of them is closed. The key to parallel switches is they provide alternative paths for electrons to flow. Either one of them will allow the circuit to be completed, as you can see here. Now, one way I'd like you to think about that is that we can say that switch 1 or switch 2 can be closed and we'll have a circuit. And since switch 1 or switch 2 can be closed, the key word really is or, because switches in parallel correspond perfectly to the OR operator, or Boolean addition, or the plus sign. So this is one of our two fundamental relationships for today. Switches in parallel, like they're shown on your screen here, when the two switches run side by side, switches A and B, we would say that either A or B conducts electricity, or in terms of Boolean algebra, we would say that that's A plus B, since you know that the Boolean operation of addition corresponds to an OR condition. Now hopefully that's consistent with what you learned in the previous lesson, because as we can see in our little animation here, in Boolean algebra, 1 plus 1 is 1. That is to say both switches are closed and we get current flow. 1 plus 0 is 1, which means if one is closed and the other is open, we get current flow. 0 plus 1 is 1, which means if one is open but the other is closed, we get current flow. And of course, 0 plus 0 is 0. That is to say, if they're both open, we get no current flow. And you can see that by watching all four conditions of our two switches in this circuit. The other way that switches can be arranged is in series, that is to say, one in tandem or following the other. Switches in series will only complete a circuit when they are both closed. You can see that in the animation here. If either one is open, the circuit is broken, but when they're both closed, then we have electricity flow. Now the key word there is and. Switch 1 and switch 2 have to be closed in order to allow current flow, and that's why switches in series correspond perfectly with the AND operator in Boolean algebra, or in other words, with Boolean multiplication. And as you can see in a simple representation of switch A and B in series, electricity is only going to flow through those switches if A and B are closed. And the key here is the representation. Switches in series are not running alongside each other. They run in tandem with one another, one flowing right into the next. And hopefully that's consistent with what you learned in your previous lesson about Boolean algebra. We have four possible outcomes with two switches in series. 0 times 0 is 0, of course, because if both switches are open, we get no flow. 0 times 1 is 0, that is to say if one is open and one is closed, we still have no flow. 1 times 0 is also 0. Again, one open, one closed, no flow. But 1 times 1 in Boolean algebra is 1. That is to say, when both switches are closed, that's the only way we can get an outcome of 1 or have current flow. Okay, let's take a look at an example here. Let's draw the circuit A plus B plus C. Now that's Boolean algebra. Of course, that means A or B or C. And determine whether or not there's a path to complete the circuit when A is a 1, B is a 1, and C is a 0. Okay, let's get started. Well, first of all, recall that the operation of addition in Boolean algebra represents OR, which we represent by a parallel circuit. And so since we have A or B or C, that means that the path for switch A, switch B, and switch C will all be in parallel. So we're going to have one path coming in, and that's going to split into 3 separate parallel switches. We'll have a switch A, switch B, and switch C. Now, we don't always draw the gates on those switches. That is to say, we can also represent that by simply saying we have our 3 paths, and A, B, and C. So we don't need the little toggle or flap within those switches. We can get the idea here. So that's all there is to it. A or B or C means that electricity can flow through A to complete the circuit, or through B to complete the circuit, or through C to complete the circuit. And we're done. Now let's determine whether or not there's a path to complete the circuit when A is closed, B is closed, and C is open. Well, you can see pretty clearly that if we close path A and close path B, but leave C open, yeah, electricity will easily flow through A and B, and in fact, we don't need both of them to be closed. The whole point of the OR operator or Boolean addition is it only takes one to provide a path. And so we can conclude that under the given conditions, electricity will flow. Now I want to compare that with a very similar Boolean expression. What role do parentheses play? Let's draw the same circuit, A plus B plus C, but we're going to put parentheses around A and B. And we'll determine whether or not there's a path to complete that circuit when we have a different set of criteria. A is open, B is closed, and C is open. Okay, well the fact that A and B are in parentheses means that we should start by drawing A and B in parallel. So we're going to have switch A and switch B in parallel. Now, those two form one parallel path, or C, so we can have A or B, but we're going to have another option alongside of that, and that is C. Now, is that really the same thing as we had in our last circuit? Well, fundamentally, yes it is. Our electricity can come in, go through A or B or C, just as it can here. It can go through A or B or C. So what we're starting to see is that there's a slightly different representation for the exact same circuit, and that's sort of where we're headed with this. How can we simplify complex circuits? That's what we'll work on in a later lesson. So here's our circuit. Now let's determine whether or not there's a path to complete this. I want to note that even though we've drawn our circuit, we don't have to draw the light bulb and the battery and the other half. We're really only interested in drawing the switching part of the circuit. The rest of it is sort of given. Now, if A is a 0, that is to say open, B is closed, and C is a 0, which is open, that means that B is a 1, A is a 0, and C is a 0. What's our outcome here? Well, you can see we've got a path to flow right there, and so electricity will flow here as well. And in fact, we could say that the outcome of this, when A is 0, B is 1, and C is 0, we can conclude that our output here is a 1. Now I'd like to have you try one for practice. Draw the circuit A times B times C and determine whether or not there's a path to complete the circuit when A is 0, B is 1, and C is 1. Take a minute and do that. Unpause to see that solution. So if we want to draw A times B times C, what will that look like? We have to have A and B and C be closed. These are switches in series and not in parallel. So we're going to have switch A, switch B, and switch C, all right in a row. Now we can also represent that by leaving off the toggle flap part of the switch and just put ABC, and that's a simpler representation. There it is. That is A times B times C. Now, will there be a path when A is 0, B is 1, and C is 1? That means B is closed and C is closed, but A is open? No, you can see that any one of these being broken breaks the entire circuit because we have to have A and B and C closed according to our Boolean logic, because Boolean multiplication means and after all, and so we can conclude here that electricity will not flow. And so the overall outcome of our circuit here is a 0. We have no flow, which makes sense because 0 times 1 times 1 in Boolean algebra is 0. So what if you put parentheses around the B and C? So we have A and parentheses B and C, or in other words, A times B times C. Well, we would start out by drawing B and C in series. That takes care of our parentheses. Now A is in series with that pair, so we would put A out in front, and you'll say, hey, that's the exact same thing we had a minute ago. Yeah, it is. The parentheses make no difference here. That's not to say that parentheses don't matter. In our next lesson, we're going to see that parentheses matter a lot, but those are going to be some more complex expressions. Now, is there a path when A is 0, B is 0, and C is 1? C being 1 means C is closed, and so do we have a path? Not at all. A and B are both broken. Electricity will not flow. The outcome of that circuit is 0 because 0 times 1 is 0. And one last question here. Determine whether or not this circuit will allow electricity to pass under the following conditions. A is open, B is open, and C is closed. Take just a minute, look at that circuit, and determine if that switch network will allow current flow. Well, that one shouldn't take you too long. A and B are open, but C is closed. So if we close the switch C, you can see that electricity still has no path. It's going to have to find its way either through switch A or through switch B, even to get to switch C. And so our circuit will not conduct electricity. Now, if you look careful at this, though, switch C, you might notice, kind of turns out to be irrelevant. Because if we're going to have electricity flow through C, it's also going to have to flow through B. But if B is closed, then it could just go through the top switch B, and it wouldn't even need switch C. So switch C on its own really has no impact on whether or not we'll get electricity flowing. Really what matters is will electricity flow through A or B. And that just proves that this circuit is actually more complex than it needs to be. It could be simplified, and that's the topic of one of our next lessons. Okay, well that wraps up this fairly short lesson, but there are some really important concepts that we're going to use going forward. Let's review those quickly. Fundamentally, we view Boolean algebra through visualizing it as a circuit. And one of the three main things you need to know is that a 1 in Boolean algebra represents a closed switch, whereas a 0 represents an open switch. The Boolean operation of addition is represented perfectly by two switches that are in parallel, which means that electricity can flow through one switch or the other one in order to have current flow. And the Boolean operation of multiplication is represented perfectly by two switches that are in series. That is to say, we have to have both switches closed in order to have current flow. We have to have A and B closed in the picture that's on your screen. So make sure to do the homework for this section. Fairly short homework and important topics, but we'll build on this by looking at more complex switching systems in our next lesson. We'll see you there.